By studying fire, both fire behavior and fire effects and the smoke that comes from fire, we're able to provide society with ways to fight fire or to use fire to our advantage and to manage fire so that it won't affect people and property as much as if we couldn't manage it.
The Fire Lab is 55 years old. I was here in 1960 when it was established, and the chief of the Forest Service dedicated it. The city band was out here, and I was a little 7-year-old kid sitting in the audience watching it. It was one of 3 labs nationally that were established for this as part of the research branch of the Forest Service. And research and development in the Forest Service is organized around 7 geographic areas. We're in the Rocky Mountain Research Station area, and that's the 12 interior West states. So we're the only fire lab in the 12 interior West states. We organize our science here at the lab in 6 focus areas. So we have a very elaborate research facility here, probably the most complex and unique combustion laboratory in the world with our combustion chambers and our wind tunnels. So while it's a laboratory and we do this physical fire research in our facilities, many of our scientists and their staff are actually out in the forest and woodlands doing work on fire ecology, fire history, fuel management techniques, looking at different ways to manage forest restoration to support more resilient forests.
The surface wind modeling that we do helps us learn about how wind affects wildland fires, in that especially terrain. So terrain has a big impact on the wind flow. So wind speeds up to stronger speeds at the tops of ridges and slows down on the back sides of ridges and things like that. And so that's what our wind model primarily does, is look at how terrain affects the wind flow. So surface wind modeling is some computer models that we've developed to predict the wind flow near the surface of the ground, and primarily that's to drive wildland fire spread models, because the spread of a wildland fire is really affected by the wind speed. So changes in wind can really change the spread rate of a fire.
All of my research is basically focused on understanding how wildland fuels both ignite and burn. So I've got projects looking at everything from critical conditions for ignition to looking at how the heating mode changes how things ignite, and also looking at what the burning rate and residence time is of a flame in a given fuel bed. So a crib is an ordered cross pile of sticks. So they basically just look like little Lincoln log houses. But what's really interesting about them is that you can build them in any kind of shape and arrangement with any kind of different fuel sizes. So we can really get a glimpse into exactly what parameters affect how a fuel bed burns. And though they don't look like wildland fuels at all, the underlying physics of it is really vital to understanding how something like a wildland fuel bed will burn. So they're giving us an insight into the sort of the deeper problem and a deeper understanding.
Yeah, so we study flame structure using artificial fuel beds. It's very difficult to study flame structure using natural fuels because there's so much variability in grasses or in understory fuels in forests or shrublands, and so much variability in the weather, in the terrain, coupled with the fuels out in the wildlands. So in the laboratory, what we do is we try to isolate these sources of variability and limit them. Wherever you see a parcel rising in one of these peaks, what you also see is a parcel that's descending in the trough. Okay, and so this is what makes this very regular pattern of upward rising peak of flame and then a downward descending trough of cool air. And it's in these troughs where most of the heat transfer is taking place. It's kind of counterintuitive, but wherever you have cold descending air, it's actually pushing the flames down into the fuel bed and pushing them, splattering them out into the fuel ahead.
I study fire ecology and the general impacts of fire on forested ecosystems. By coring trees, we can look at their ring patterns and we can see how the tree is responding to a fire or responding to some other fuel treatment such as thinning. It's important to study because how fuels change over time will then affect how a fire behaves when an area does burn.
Well, one of the things we focus on in our research is smoke characterization. And by smoke characterization, I mean we try to figure out what's in the smoke, what are the chemical compounds in the smoke. We do that through a combination of laboratory experiments, and we bring in stuff that typically burns in wildfires or prescribed fires. We bring those fuels into the combustion laboratory, and based on what we learn in the laboratory, we have an idea of what chemicals are in the smoke. That helps us understand what happens to the smoke and how it produces additional pollutants. The impacts from wildfires are much more significant, both in the magnitude, how much smoke is produced, how thick it is. Because wildfires produce a lot of smoke, smoke can be transported very long distances and still be concentrated enough to have negative air quality impacts, literally hundreds of miles, and sometimes even 1,000 miles away from the source.
Daylighting is a technique that we use for an ecological restoration to release trees that we want to save on the landscape from competition from other trees. And what this entails is going out and finding the trees that we want to save or to keep, and then cutting around that tree a certain radius or distance so that we can remove all the other trees, including the saplings and seedlings, so that this tree can grow without competition. So what would happen then is if we get a fire when there's shade-tolerant trees, it's a crown fire, and it's very bad for people, and it's bad for the ecosystem.
I work with the Fireworks program, which is an educational program designed to teach about the science of wildland fire. Fireworks activities are primarily used with students kindergarten through 12th grade. And so for each level, we use different sorts of lessons. So for example, with younger students, we use felt boards to tell the stories of fire. And with older students, we use physical models and theoretical models to teach about fire spread and how fires scar trees. Matchsticks Forest is an activity that we use to teach students about how fire spreads in wildlands, and particularly how fires spread on slopes. So we use this as a physical model to represent our activity. Can you feel the warmth? Yes. So now our trees are burning. We have a little bit of wind, which helps it spread. Students they're the next leaders in the future. They will be our next land managers, and they're going to make the decisions about how to manage our land. So it's incredibly important for students to understand what goes on in their ecosystems.
Wildland fuels are an amazingly complex and complicated ecosystem characteristic to study. Number one, there are many, many types of fuels, from grasses to forbs to downwoody that are on the ground, to litter that's on the ground, to the duff that's below the litter, to canopy fuels that are above. In the fire models, we need to know what the surface area to volume ratio is of each fuel type. We also need to know things like heat content and the size and shape of the fuels in order to understand how they burn. All of these properties and the fuel types change incredibly over time.
The solutions involve more fire, not less fire, but fire under our conditions at our time and place of choosing.